So let's move to the first example. So when you start with the newtons, you have to explore with the system whether this system have the resultant force or not having any resultant force, which is in this case it look like the traffic light hanging like this stay still. So this is the reason that uh, force that acting onto like this knot, you can see the string tension is kind of like force that pulling the weight of these light bulb or traffic light, not a light bulb, sorry, it's a traffic light. This is not longer using here in Thailand, but I think like in some countries they may use like the sling like this sample. So you can see this system as in equilibrium or stationary state, not moving, so that you can apply the first law of Newton's, the law of inertia. So that means with the sum or the resultant of the force, there's no acceleration, there's no net force involved in this system. And what you have to do, if you look after to this system, you have to think about the key object that you're looking after, which is the first object that you look after is your traffic light. Another thing is this knot. This is kind of important thing that you have to figure out. Why to figure out things like that? For example, like if you're looking after the object 1, I will show you how to draw the free body diagram later in the detail, but this is how you mimic what is happened in the situation of the problem and try to break the system and illustrate step by step. So you can have the first object as the traffic light, and you see the weight of this traffic light, or this writing like FG, which is mg of this traffic light pulling downward. There's going to be another force that hang it or pulling it upward. So that force is the string tension, right, of this string. If you're looking after any object, you draw the string tension out of that object. This is the reason of the third law of the Newton. We can explain this later, but since we already know about the first law of the Newtons in the stationary state, I will show you here and try to derive it. And this is the part of vector components, which is you have to break a component and sum it up to make a resultant force as zeros. Okay, with the first object, with the traffic light, you have the upward force as string tension. The downward force is your gravitational force, or mg. For the second object is the knot. The knot here are the thing that looks stationary. It's not moving up or down. It stays still like this, but it's comprised with 3 forces acting on this knot. So they have a T1 force, T1 force over here, T2 and T3. If you look after this object pointing the string tension out of the object, this is the key that try to avoid the ambiguity of the system, that when you would like to break out and redefine it, especially in the string tension. So this is your T3 and T1, T2 and T3. So you have 2 objects. So what is this question? This is asking about like, is there anything possible to have this cable break, and how it can be capable of holding the traffic light like this? So what you have to determine, all the condition, especially the force, the net force that acting on each string. Since you now know the weight of the traffic light here is equal to 122 Newton, and you know all the angle that relate to here, the key problem is said about the string tension will break if all the string exceed than 100 Newton. So string will be break if the force over 100 Newtons, which is this force are all tension, right? 1, T2 and T3. This is the key of this problem. So you have to check how about all these force weight. So from the first object, when you look after to this traffic light, you see the force upward direction is balanced. There's no force on the horizontal forward or backward direction. So you have a sigma Fy equal to 0 in the first object. This is the object that you look after. So with this case, you have seen the T3 is equal to your mg, which is 122 Newton. This is look serious, right? And so this is in danger. Or in danger, if you say it. So it look like in critical state. So how about on the next object? If we look after the second object, which is this knot here, you will see that the resultant force is 0 as well, because there's no moving of this knot. What you can do, you can sum in x direction and in y direction, or each component gonna equal to 0 because there's no moving on the x direction or y direction. How can you break these components? So we will break the component out here. What you have known, you know about the 3T already, right? This is 122 Newtons. If you would like to break T2 components, this is T2 cos 53. This is T2 sin 53. And how about this one? This is T1 cos 37. And this is T1 sin 37. So now you can sum up along x-axis and y-axis. So the first one is your T2 cos 53, minus T1 cos 37. This is equal to 0. And how about the next one? You got the summation in the y direction, which is T2 sin 53 plus T1 sin 37, and you subtract with T3, which is on downward direction, is 1, 2, 2 equal to 0. So now you got 3 main equation, right? Like this is your first one, this is the second one, and the third one. I will always write like this because I already used the number quite a lot. So this is your I, this is your I, and this is your I. So now you got 3 different equations. So now you can solve for finding the individual, or you can sub in for the value that you want. So from the I, now you have the form of T2 in T1, which is T2 equal to T1 cos 37 over cos 53. Since you know all these angles come from the right angle, I will find a position to write it, maybe over here. Look, the critical word out. So think like here. Thinking this as your right angle. and you got other side like 3, 4, 5, right? With this different angle is linked to angle 35 degree and 53 and 37 degrees. So how can you link from this information to the one below? This is your 37 degrees and this is your 53 degrees. If you would like to find the cos theta of 53, the cos is the closest one to hypotenuse. So your cos is 3/5. This is cos 53. This is 53. Oh, we write it properly. 53. If you like to find the cos 37, this is your 37. So if the cos is the close one to the hypotenuse, so this is your 4/5. So how about sine? If you like to find sine 53, so it's 4/5. Right? And if you like to find sine 37, it's 3/5. Yeah. So that you can take all these value in. So now this is your 4/5 and 3/5, which is finally you get the 4/3 of T1. So you can sub equation 2 into the equation 3. So what you're gonna get? You're gonna get 4/3 here. You sub into this term, right? T2 and T1 that multiply with 4/5. And now you plus T1 with 3/5 minus 1, 1, 2. So finally, if you rearrange this term and try to sum it up, you're gonna get the value of T1 and T2 out, because now you already know the T3 already, right here. So when you do like the algebra on this term, so finally you will get T1 equal to 73.4 Newton. And how about the T2? If you know T1, you sub T1 into this, and you're gonna get the T2. Finally, you're gonna get T2 equal to 97.4 Newtons. And this is what you get all the information. And what this question asking you about, whether this string will break, because they said these upper cable are not also strong as the vertical. Okay, so that means this one is fine. The 3T is strong. However, this one is weak. The weak one. This is also the weak one. And the weak one is only T1 and T2. Cannot go further or exceed 100 newtons. So in this case, you can see T1 is 73 and T2 is 92. So what you can answer to this? So it still remain hanging. It's not breaking. This is the first example in the equilibrium, and you use the resultant force and the force component that you did learn from the vectors chapters, and you can apply with this problem. So next is about the gravitational force or weight. As the definition, so you know when the object has been act with the resultant force, it's moving with acceleration. Vice versa, if this object has some acceleration, which is for example like a downward acceleration as a g, if it has downward, you know the g has the negative sign in j direction. Is this your j? This is your I. Right? This is the reason that the apple has has dropped down to Newton. I'm not quite sure whether it's on Newton head directly or just drop on the grass ground. I think it maybe next. But this is how Newton thinking about there are going to be some force that attract to the apple, which is nowadays we know maybe in the more difficult field of the time and space curvature that may introduce to this interaction. But in early of that time, the Newton's law of gravitational force is quite important to determine that, as I said, when the force acting on the object, which has the mass m, is come with the acceleration. And if this object has the mass m and pulling down with the acceleration, so that's going to be some resultant force acting to it. That force we call the gravitational force. With the definition of the gravitational force, if this object has pulling by Earth, this is like big M due to the Earth and the smaller m due to the satellite. With the distance away, you can see the relation of the force attraction in terms of r square, inverse of r square. With this relation, that means when the object is go further, the r is higher, the force is lower. So when you think about the object that really close, or the r is really close to the surface, you can use this constant, the g, for the universal gravitation. This is the Earth radius, and m is the mass of the Earth. This you can find the constant of this term here, g m over r square, which is equal to g e m over r square is g. So the magnitude is 9.8 meter per second square. This is the gravitational acceleration on Earth. With these g factors, if you have the mass that really close to the surface of the Earth, with the mass and acceleration, it's force. And that magnitude of force, we call it as a weight. That's how we have the weight when we stand on the balance and check whether we have the any obesity effect or should be diet due to the gain of the weight. That's how the interaction of mass and gravitational acceleration do together. Thing is, if you would like to lose the weight, you can change to another planet to have the lower gravitational acceleration. That means you lose the weight, but your mass is still the same, right? So that mass and weight is different in this term, because mass is what is represent your own body and not relate to any gravitational acceleration. But when the weight is related to that g, whether it's on Earth or on the moon or on the planets, right? So that is the definition. So the mass unit is in kilogram, but the weight unit can be newtons, because weight is another term of force, but you're looking only magnitude of it.